Hello, everybody. So I won't spend too long on this side, but basically we've had two typing approaches for languages predominantly, and they have different kind of opposing strengths and weaknesses. So statically typed languages are good for early error detection, fast compilation, but sometimes they're a little bit rigid in that the type checker impedes your ability to kind of develop your programs. Dynamic typing is simple in the fact that you can kind of prototype easily, and it's flexible in that you can reason outside of the type system when you need to, but the lack of type information makes a lot of implementation slow, unfortunately. And so hopefully with gradual typing, what we want is just the good parts of these two things and kind of to get rid of the bad parts. But unfortunately, we kind of end up over here where we end up with the slow portion of gradual typing because enforcing soundness, as Ben is kind of going over, can have a lot of overhead. And this kind of impacts a key goal of gradual typing, namely that we should be able to kind of use the typings as we want and migrate our programs easily. So I could start with a dynamic program that I feel is stable and that I've tested it a lot and start adding type annotations to kind of get more static checking and early error detection. Or maybe I start with a static program and I'm going to add a lot of new functionality and I don't want the type checker to kind of impede my ability to prototype. So I come down here and kind of remove typings from my program so that I can more easily prototype. And regardless of kind of which direction you're going, dynamic to static or static to dynamic, you can end up along a path where you hit these typing configurations kind of in the middle where your program experiences huge slowdown. And this is kind of like taking a bad route when you're trying to get a destination and ending up stuck in traffic. And maybe along a different path, you actually experience some speed up, and so it would be preferable to go over there instead. And the worst part about all of this is kind of a lot of the times as a programmer, we wouldn't know until we started kind of trying these typing configurations ourselves. So there's a lack of reasoning about how our types kind of affect the performance. And so this leads us, maybe as a programmer, I might have different migration scenarios in my head. So one might be that I just kind of prioritize static typing. So I just want to kind of add as much static checking into my program, regardless of what the performance overhead is. Maybe I'm used to dynamic typing and I've kind of adopted this gradual language and I don't really care about my typing guarantees quite as much and I just want to make sure I don't get this performance degradation. Another thing might be that I want to kind of get the best of both worlds. So I've added some typing, seen some performance degradation, and I kind of want to get more static checking if possible, but not if it hurts my performance anymore. And lastly, maybe as I'm kind of migrating here and changing my types, I want some tool to kind of explain to me like why I'm getting these overheads in my programs because I don't think types should maybe affect my performance that much. So we're going to focus only on scenarios 2 and 3, but all four are in the paper. And so to kind of illustrate these scenarios, I first want to kind of illustrate this performance lattice possible for a spectral norm program. So basically, we can kind of move adding types to these three functions in our program around. So at the configuration labeled 3 here, I have function 2 annotated, but functions 1 and 3 unannotated. And I can kind of fill in the dark circles and end up with more static type annotations. But what I really want to illustrate is that indeed certain migration paths have a lot of performance degradation. So if I start adding annotations to function 1 in this program, I get these severe kind of performance penalties. And on the other hand, annotating function 3 and function 2 together, I kind of have this good performance over here. So if one of my migration scenarios is just to maximize performance and I'm kind of at my dynamic configuration, then I want to get to configuration 7 over here, which kind of minimizes the runtime. And then maybe if I want to maximize performance and type safety and I've kind of already added a type to get to configuration 2 and hit this overhead, I say, oh, you know, I want to keep adding types, but not if it really impedes the performance anymore. And we can see that configuration 8 is ideal here. And we want to go there because it adds static types and also minimizes the runtime. So this comes to our fundamental question here, which is basically, how can we decide kind of which configurations are better for each migration scenario? So how do we kind of rank what you want to do and then think about the performance? And so what we want is some kind of a compile time tool that supports our migration scenario. So we don't want to have to manually kind of produce these typings ourselves and you know, run them and then see what we want. We want something that can do this quickly. And this tool needs to be kind of guided in mind that existing research has shown that when you start mixing static and dynamic typing, these inserted casts in the program are what cause the overhead, especially in the higher order cast semantics Ben talked about. And so we want our tool basically to kind of statically measure the cost of these inserted casts, so to approximate the overhead of like a different cast in my program. And so to do this, we adapt basically existing cost semantics, but instead of kind of counting execution steps, we're just going to try and count the number of casts that are evaluated. And then after we kind of use this cost semantics to compare the cost of all of our different configurations, we can kind of guide you towards your ideal configuration for your migration scenario. So with this, we've kind of developed this idea of a cost lattice that corresponds to your performance lattice. So basically for each configuration, we will replace the kind of runtime with these cost expressions. And you can, for now, just read these B, C, and G as just like large constants. But what I really want to show is basically that we have these kind of large costs here that are approximating overhead, and they're large at the slow areas, and they're small at the fast areas. So for the migration scenarios I outlined earlier, for example, scenario 2, maximizing performance, where I started at the dynamic program, the kind of smallest cost in the rest of the lattice appears at configuration 7, so that's the one we want to go to. So we use the cost to kind of guide you there. And similarly for the other scenario, when I wanted to add it static typing, but not if it added overhead, I look at 5, 6, and 8 and compare them to the cost of 2 and see that 8 has the lowest cost and adds the most static typing, so that's where I want to suggest you migrate to. So now the question becomes, how do I kind of mechanically produce these cost lattices in an efficient manner, especially because, as Ben showed, there can be a lot of configurations we have to consider. So just to illustrate why a naive solution is bad, we might just say, like, okay, let me take my source program with n parameters, do a single gradual cost analysis on like the current configuration and produce one cost, but now I kind of have to go and keep changing the types. So I repeat this process 2 to the n times before I can finally start to kind of compare all the different costs. So instead, kind of inspired by variational typing, which can kind of do this considering exponential spaces in a more efficient manner, we basically instead do one variational cost analysis and directly produce 2 to the n costs. So our overall solution is that we can support these migration scenarios by efficiently kind of producing and analyzing these cost lattices. So just to give you some kind of background into how preserving soundness has overhead, consider this add function where we have 2 parameters, x and y, that are dynamically typed, and a plus operator that expects 2 integers and returns an integer. In order to preserve the soundness of this program, we basically compile it to a cast inserted program where these 2 casts appear that are runtime checks protecting the type code. So basically on x and y, we check these 2 to make sure that they are indeed integers before they're passed to the plus operation. So if I start calling this add function over and over with integers, then I'm kind of unnecessarily running these 2 checks over and over, especially if I'm in a tight loop or something, by the time I get to this plus operation, and this causes a lot of slowdown. So the question becomes, how does kind of, me changing types in the program affect the number of casts that are inserted, especially as we've seen that like sometimes the boundaries have certain properties. So let's just consider adding one annotation to our program. So we can add the int annotation for x, and in the cast inserted program, we're basically saying that, okay, the type checker has verified that this x is indeed statically typed, so we don't need a cast here. Similarly, we can just add an int annotation to y, and then one cast just appears on x. And kind of our best version of the program, at least for add, is basically to add 2 annotations to x and y so that I end up with no cast in the body of the function, although it might be the case that if add is receiving dynamic arguments, I've kind of just moved it to the application sites. But for the sole purpose of optimizing the add function itself, kind of this is the best scenario because we have 0 cast in the body. And so now our idea is that we need to kind of count these casts as type changes, and we need to do this efficiently. So we're going to kind of encode the way types change with these things called variational types. So basically, I have these 2 variational types that have a unique name, B and D, that are associated uniquely with the parameters x and y. So B associates with x, D associates with y. These things have basically left and right alternatives, which are the like subparts of it, where we have the dyn type on the left and the int type on the right. And we can kind of project the left and right alternatives out of our variations, similarly to kind of projecting out of a product, except that we now have a unique name. So basically, the selector b.1 only selects out the left alternative of b and does nothing to d. But regardless, if we kind of use both selectors and provide the selection process on our variational program with B1, D1, we end up with X and Y being unannotated. And going all the way to B2, D2, we end up with int annotations on both X and Y. So now we need to kind of encode how the casts are going to change as we start kind of varying the types. We should also vary the casts inserted into the program. So we have a process now called variational cast insertion, where now I have a variational cast here that corresponds to my variational type, where basically, if we select the left alternative of B, where X is dynamically typed, then we actually insert a cast. And if I have the kind of right alternative with the int type annotated on X, then I have this epsilon, which denotes that no cast is actually going to be inserted into the program. And so now I can kind of consider the selection process on my variational cast program. Selecting B1, D1 basically puts the actual casts into the compiled program. And going all the way to B2, D2, we don't insert the cast in the program because this was the version where X and Y were statically typed with int annotations. So now kind of the question becomes, how do I directly calculate the variational cost for this expression? So basically, I have these two variational casts here, and I want to directly kind of count things and not actually separately count them. So I need a corresponding variational cost. So the cost for this expression is basically just the sum of the sub-expressions costs. And so we kind of end up with this left sub-expression that we'll consider first. So here I have the variational cast on X, where I have a real cast being inserted on X when it's dynamically typed, and no cast on the right here when I'll be treating it as statically typed. So I can kind of just take this counting that I'm doing here and directly encode it into a variational cost. And you can see that I have the 1 on the left for the one cast that's inserted in the dynamically typed, and 0 on the right when no cast needed to be inserted. So I move on to the right sub-expression. And basically, it's the same thing that happens here, except now we have a Y and a D. So then I kind of go and I want to add the cost of these two sub-expressions together. You don't need to worry about this. This is actually just kind of a simple distributive approach. But basically, I end up with this final variational cost with a 2 all the way to the left, kind of indicating that that was the dynamically typed version of the program with the parameters, and I inserted 2 casts. And the 0 all the way to the right is when it was fully statically typed and I didn't insert any casts. But I want to show you that indeed these variational costs kind of respect your real costs. So let's consider this 2 here in my variational cost. To produce this 2, I need to provide the B1, D1 selector. So when I select this on the variationally typed program, indeed this corresponds to the version where X and Y were dynamically typed. And then when I select on the variational cast inserted program, we do end up with the left alternatives of those variational casts being selected out. So we end up with those 2 casts. So you can see that the 2 cast lines up with the 2 costs and the variational cost. And so similarly, I kind of go all the way to B2, D2, add both of my int annotations. No casts kind of appear because I was selecting out those epsilons in the right alternative. 0 casts respects the 0 cost there. So now that I have this variational cost that kind of represents my cost lattice for the program, the question becomes, how do we find the best performing configurations? Simply put, I can kind of just individually select out all of the costs and rank them, and then kind of order the selectors according to that. So I see 0 is the smallest cost for this function. So B2, D2 is kind of the selector I want. Then I recommend the configuration add with 2 statically typed parameters since B2, D2 produce the smallest overall cost. But quickly, I just want to kind of illustrate that in general, this process isn't that simple in that I have a lot more than one function definition that I'm kind of trying to optimize, and that it doesn't end up being the case that I can just kind of keep adding static types and that will remove all the casts because maybe there's parts of the programs that I don't know how to add types to, or like it has eval in it or something. So this ends up being a much more complicated process. And there's a lot of other kind of features that really challenge the ability to do this cost analysis in a simple manner. For example, higher order casts that can kind of create more casts later, inserting a cast in a loop or in a recursive function, et cetera. And that in section 4 of the paper, you can kind of see how we address these challenges and how we connect the cost analysis to the number of casts that will be executed in a single configuration, so not considering how I can vary things. And then section 5, I basically kind of lift this to using variations everywhere with the variational typing, cast analysis, cast insertion, and cost analysis. And all the meta theory is in those sections as well. So what I really want to get into now is basically these performance results. So I basically took like 13 benchmarks of varying sizes, and then I had the tool basically find the lowest cost to support the migration scenario 2 from earlier, which was just maximizing performance. So we basically wanted to see if our cost analysis was accurate. So I timed basically our tool's pick for the configuration, and then I sampled randomly because these spaces might have a lot of different configurations, you know, a large subset of the overall configuration space, logged their times, and then saw whether or not our basically tool's pick was one of the top 3 best performing configurations, as in it had the lowest runtime since we want to maximize performance. And yeah, 12 out of the 13, it was indeed one of the top 3. It was the #1 pick in several of them. And even the one we weren't in the top 3 for, we didn't have that much overhead. And moreover, compared to the random kind of pathological cases that you might run into when migrating manually, our picks performed 3 to 5 times better there. So yeah, the major results I want to get into is basically that we wanted to support these migration scenarios with cost lattices. So I wanted to produce these cost lattices and kind of compare the costs and see how the typings and the costs related to each other. I did this by using these variations to kind of encode the lattice structure and then kind of efficiently compare the cost between these different configurations. And then our evaluation shows that indeed these cost lattices really effectively model the performance lattices from earlier with large costs with large runtime and small costs with small runtimes. And so basically to kind of summarize the talk here, the key goal of gradual typing, or one of the key goals, was that I wanted to migrate programs easily. So as I start adding and removing types, I could not start running into unexpected performance overhead. However, in practice, I see that if I start doing this manually, I can end up with typings maybe as I'm trying to get to my point that I don't even want, and that they start slowing down my program, and that maybe if I went a different path, I'm better on the way getting the types I want and not getting these performance overhead. And so we kind of want to be able to pick the winners and the losers statically, you know, not letting you migrate to configurations that don't meet your goals and letting you get to the ones you want. And that basically we kind of implemented this by efficiently producing these cost lattices that we could then analyze and compare configurations for so that we could support your migration goals and get you to the kind of typing desires and performance desires for your program. And that's it.
Okay, so there are several related questions on the understanding the lattice. So you mentioned in your talk a bit, but
yeah.
I think it might be good to re-insist. Why is it that a fully statically typed program can be slower than?
Okay, right. So the fully statically typed program in this case was just in reticulated. You can only add types kind of to your parameters and the return types of your functions, and you can't kind of like add static type annotations in the body to variables. And also in the fully static kind of version, that was just you adding types to your functions, but like you could call external dynamically typed libraries there. So it wasn't necessarily that your program was fully statically typed, just as in you added the most amount of typing to what you could handle there.
So do you actually need to provide all configurations ahead of time before your tool can pick the best migration path?
No. So we use type inference and kind of work with a subset of Python. So there's certain features that we kind of don't really handle all the way, but no, the idea is that we use type inference kind of from the dynamically typed configuration, and we use error-tolerant typing to kind of go and explore this configuration space and see what we can actually infer of the overall kind of lattice there, and then consider just that part of the lattice which we can infer, which is usually most of it, depending on the structure of the program.
So what language were your experiments?
So all the experiments were done on reticulated Python, specifically with the guarded semantics, or in Ben's terminology, the higher order semantics.
So how do you ensure that the variational technique doesn't blow up exponentially? exponentially?
So
Like
previous work on variational typing and gradual typing has shown that like this could be done very efficiently because large parts of the typing process are repeated, and like only adding just like a type here or there, you kind of still share a large part of the typing process. With variations, with the cost specifically, there is a lot more overhead because you start like adding one kind of cast here or one cast there. So you kind of can run into, for very large programs, this exponential blow up. But depending on the structure of your application, or if you're just trying to like optimize at the module level, you can kind of get away with this more.
Okay. Can you clarify the semantics relating to the previous talk? Which of the three semantics you are?
Right. So it's the higher order semantics is what we configure. So you would install like proxies on functions and such.
Okay. So one question is whether what happens with type-directed optimizations? Can your model be extended to take them into account?
Oh, as in like consider that you're using the types to provide some kind of optimization away? Yeah, so right now we're kind of naively assuming that like whatever types you're kind of inferring there, you're kind of immediately inserting these casts and that nothing is kind of optimizing the way like a JIT or anything behind the scenes. But I suppose it could be possible that we could maybe try and consider that in the cost analysis if we knew what kind of, the compiler did exactly.
So finally, so in your experiment, what was the balance of typed and untyped boundaries that the tool suggested?
Yeah. So I feel like a lot of the time, sometimes it was closer to the extreme. So it would usually be closer to the static extreme or the dynamic extreme. But there were some examples where like a lot of it is kind of particular to reticulated structures, but you actually might have a middle configuration. So like the 7 here is close to the top. But there are certain things, like even the dynamic version, that like tuple unpacking and things that insert casts. So even if you're not adding types, you're still having these casts here. So sometimes the dynamic extremes actually aren't that good. So like you can see here.
Okay. Thank you very much.
All right.